All right, well, I have some good news. I think you're going to like this news.
Really?
We are done with volume.
Huh?
Yeah! And we're not even going to have any quizzes or tests on it.
Yeah!
Now, you are going to have a lot more with volume next year.
No.
So it was good that I had the chance to introduce you to volume, make sure you saw how it worked, taught you some formulas. It'll make next year easier if you can retain it. But you're not actually going to be quizzed on volume, tested on volume. We are transitioning out of that, save that for pre-algebra next year. We're going to transition to some actual algebra concepts.
No.
And if you would flip back in your books all the way back to page 101, you may have noticed we skipped chapter 3. And we were saving it here for the start of the third quarter. So let's come back to chapter 3 now. We've covered 1, 2, 4, 5, 6. Let's hit chapter 3 now. And I want to start, though, by just doing some basic math review, some stuff that we covered in the first 2 chapters. One of the things is you look at the bottom of page 101, it says to circle prime numbers. Whew. It's been a little while since we've talked about this. What are prime numbers? Bryson, do you remember? Can you give me an example of a prime number?
8.
Is 8 a prime number, class?
No.
No, because how might we factor in 8?
2 4.
Okay, so in other words, there's a way to factor it besides 1 times itself. And that's what a prime number is. A prime number is a number that only factors into 1 in itself. See, I told you it's been a while since we talked about this. So now can you think of a number that you can't split up other than 1 in itself?
2.
Okay, 2. All you can do is 1 and 2. There's no other way to split it up. Kirsten?
7.
7. All you can do is 1 and 7. There are no other ways to factor it. Corey?
11.
11. Also, only 1 and 11. No other ways to factor it. And I had us memorize, but it was a long time ago, our first several prime numbers. If you can remember them, say them with me. 2, 3, 5, 7, 11, 13, 17, 19. Let's say those together. 2, 3, 5, 7, 11, 13, 17, 19. Again. 2, 3, 5, 7, 11, 13, 17, 19. Now close your eyes and see if you can do it. 2, 3, 5, 7, 11, 13, 17, 19. All right, you can open your eyes again. So, as we look at number 33, we want to circle the prime numbers on the list. Take about 5, 10 seconds maybe. Do number 33, the review section at the bottom of page 101. Circle any numbers that are prime. Circle any numbers that are prime. And, Luciana, which ones did you circle?
0, 2, and 23.
You're right about the 23. You can only factor it into 1 and 23. You're right about the 2. 0 isn't prime or composite. It's just a big nothing. There's another number like 0 that isn't prime and it's not composite. It's just a big nothing. Jalen?
1.
1. 0 and 1 aren't anything. They're just there. So 2 and 23 are our 2 prime numbers. We also talked a while ago about something called integers. Integers. Integers are numbers I like. Because integers are numbers that don't have any fractions or decimals. So there's only one integer in number 34. And which number is that, Jalen?
32. -32.
Negative 32. Integers can be negative, but they can't have fractions or decimals. So negative 6.7, not an integer. 8.5, not an integer. Negative 32 is an integer. Number 35, we talked about something a while back called absolute value. Remember we talked about the number line? We said that there's this line that goes infinitely far in one direction and infinitely far in the other direction, and right smack dab in the middle of this infinite line is what value, class? Or value? 0, right? 0 is called the origin of the number line, and then your positives go off in this direction and your negatives go off that direction. So class, say these with me. 1, 2, 3, 4, 5, 6, 7, 8, so on and so forth, right? I'm not going to number all of them because I'm lazy. And then say these with me as well. Negative 1, negative 2, negative 3, negative 4, negative 5, negative 6. We'll stop there for sake of time. So if I were to ask you absolute value, does anyone remember how we define it? It's a real, I'd be shocked if we can remember this, but Kirsten wants to take a stab at it.
Like putting one line on the other side of the line.
Okay, that's how we represent it. Like if we had the absolute value of 5, we would draw these two bars on either side of it, kind of like the parallel symbol with the number in the middle. But what does it mean? Do you remember?
I have like a definition. It's like a number that has like something without fractions or decimals.
No, that's an integer. It's the number's distance from 0. How far away is it from 0? Well, class, this is 5 right here, correct? How far is 5 from 0, class? 5. How about negative 5? Negative 5 would be right here. Well, how far is negative 5 from 0, class? 5. No, just 5. It's in the opposite direction, obviously, but the negative just tells us it's on the other side. The actual distance is still 5. So practically speaking, remember, we said absolute value. You basically just ignore whether it's positive or negative and just write what the number is. So this should take all of about 10 seconds. Answer all the parts to number 35. Give me the absolute value of each of those numbers. Shouldn't take long at all. Maybe 3 seconds would have been more appropriate. What's the absolute value of 7, class?
7.
Absolute value of negative 23?
23.
Absolute value of 8?
8.
Absolute value of negative 4?
4.
There we go. We also talked about this idea of a number being bigger than another one. For instance, if I said, let's see here. Ben, how old are you?
13.
You're 13. Do we have any youngins in here? Any 11-year-olds in here? Small children? All right. All right. Anyone older than 13? You are?
14.
14, okay. All right, so who's older? If he's 13, he's 14. Who's older, class? Griffin is older because he's 14, right? And 14 is, and we use this symbol, remember, greater than 13. How many of you are 12 in here? Several of you are 12. How many 13-year-olds? Several of you, and then 14-year-olds? Just a couple of, all right, so we would say that 12 is less than 14, right? Remember greater than, less than? Basically, remember the mouth eats the bigger value. And of course, it is possible for numbers to be equal. For instance, we could say that the absolute value of 5 and the absolute value of negative 5, since they both are 5 class, equal are to each other. Which is bigger though? 4 or negative 8? Which is the bigger value, class?
4.
4. A positive is always bigger than a negative. Think of it this way. Would you rather have $4 or have nothing and owe somebody $8? Meaning the first $8 you get go to them. Well, of course, you'd rather have the $4. Which is bigger, negative 1 or negative 5?
Negative 1.
Negative 1 is bigger because you'd rather owe somebody $1 than owe somebody $5 if you want to think of a money analogy. On the number line, we would say negative 1's here, negative 5 here. The further this way you go, the bigger and bigger and bigger the numbers get. Since negative 5 is this side and negative 1 is up here, negative 1 is greater. 4 is here, negative 8 will be down here, 4 is bigger. At your seats, I want you to do number 36. Fill in the blanks with greater than, less than, or equal to. Fill in the blanks with greater than, less than, or equal to signs. Like one of the little waitresses at a fancy restaurant where instead of a necktie like this, they wear the little bow thing. Whatever. Don't worry about it. Number 36, what did we put in the blank, Elaine?
It's like this. Is that less than?
Less than. Very good. Negative 20 is less than. The mouth should be eating the 4. Letter B, what did you put in the blank, Joel?
Eating the 10.
The negative 10. So we would say it's a less than. Negative 11 is less than negative 10. How about letter C? Kirsten?
Equal to.
Equal to. Those two absolute values are equal. How about letter D? Ben?
17 is greater than the 1.
Good. The absolute value of negative 17 is 17. So that's greater than the absolute value of 1. Now, if it didn't have absolute value, class, which is greater?
1.
1 is bigger. But when it says the absolute value of negative 17, that is greater than the absolute value of 1. How many got all 4 of those correct? Any questions on number comparisons? That's going to be important in the lessons ahead. Dropping down to number 37 now. It wants you to order these numbers from least to greatest. Take a minute or so on this one. Think through which of those is the smallest value, which one's going to be the biggest value, thinking about what you know about decimals, fractions, and absolute value. Number 37. Put it back in here where it belongs. Oh. Dear Mom, please do not send hair bows with Jalen. She is too distracted. All right, number 37. What order did you write these numbers in, Michael?
-3, -2.1, negative the absolute value of 2, and 2.5.
Yeah, what is the absolute value of -2, class?
Two.
Positive 2. It was just the 4 of them? Yes. So we're going to start -3 is the smallest, -2.1 is a little bit bigger. Absolute value of -2, which is 2, would be clearly bigger than these ones, and then 2.5 is a little bigger than 2. How many of these 4 numbers in the correct order? Any questions on that one? Jalen, question?
No.
Okay. Number 38 says to solve using order of operations. Let's quickly review order of operations. We use the whatever the thing is, PEMDAS, right? And where we need to remember multiply, divide, go together, add, subtract. Say these with me, class. Parentheses, exponent, multiplication, division, addition, subtraction. And parentheses involves other grouping symbols as well. So it could be parentheses, it could be these squared off parentheses like brackets. It could even be a fraction bar. Right? If you have a fraction bar, you could put everything in the top in parentheses, everything in the bottom in parentheses. At your seats, I want you to solve number 38, A, B, and C. Take a couple moments to work these, and we'll go over them together. Wherefore, did you have too much sugar this morning?
Yeah.
It was that piece of candy you ate. No more candy for Michael.
Oh.
I tell you, can't hold his sugar. All right, for sake of time, let's take a look at these together. On the first problem, we have 2 different sets of parentheses. So inside the first parentheses, we need to simplify then.
30 plus 3.
Yeah, which is what?
36.
36, there we go. Okay, now for redemption then. The next set of parentheses,
10.
what do we get? There we go. And now, class, we have parentheses up against each other. What does that mean? Multiply. We saw this a lot, didn't we, with our volume formulas, surface area formulas, where we wrote numbers in parentheses up against each other. We know that means multiply, and it's pretty easy to multiply by 10, class. You just go boing. And so what do we get for our answer then?
360.
360. In the next problem, I do have parentheses. You just don't see them. It's a grouping symbol. And what is that grouping symbol, Kirsten?
What do you mean?
What grouping symbol do we see in this next problem?
6 squared minus 2.
The fraction bar, right, is my grouping symbol. It groups, right, the 6 squared minus 2, but it's all grouped together by the fraction bar. Now, within the grouping, though, I've got a subtraction and I've got an exponent. And which one has to happen first, class? Exponent. So Bryson, let's start by squaring the 6. 36. Then we'll subtract away the 2 to get 34. So we're going to simplify the grouping symbol to get 34 over 17 plus 3 squared. But I have another exponent. Remember, parentheses or grouping symbols first, then exponents. There's another exponent. I've got a 3 squared, Luciana. 9. So we can make this a 34 over 17 plus 9. Now I have 2 operations. We obviously see the addition. What's the other operation on the board, Corey? Division. We need to remember the fraction bar means division. Which one do we do first, Corey?
34 divided by 17.
Good. We'll do the 34 divided by 17. And even though we didn't memorize our 17 division tables, I think you know what it is. 34 divided by 17 is? 2. So we just get 2 plus 9. And finally, class, we get our answer of 11. How many have 11 for your answer on the second one? Questions on that one? Look at the next one, Griffin. Again, I see a grouping symbol, but it's not actually parentheses. Once again, it's a fraction bar. So if I wanted to, I could put everything in the top in parentheses, everything in the bottom in parentheses, if I wanted to. I'm usually lazy, so I don't. Looking in the top, though, there's 2 operations, an exponent and a subtraction. Which one has to happen first?
Exponent.
And when we take care of the exponent, we're going to get
49.
49, and then we're going to subtract 49 minus the 31 to get
18.
18. In the bottom, I have two operations. I've got a division and I've got a multiplication. Michael, which one comes first?
Division. Well,
They're technically the same step, but we will do the division first. Why?
because it's the one that comes first.
It's the one that's written first. So we'll divide first,
3,
and then we'll multiply the 3.
9.
And finally, class, we end with a division, and we end up getting an answer of 2. How many had 2 for the last one? Again, just some different things that are related to algebra that we did way back in the first quarter. Wanted to make sure we refreshed our memory just a little bit on these questions on that. All right, flip back, if you would, then to page 98. So turn a page back to the start of chapter 3. And today really is going to be about some things we've already kind of discussed most of these, but we haven't always given names to some things. So we're going to name some different things that we've been doing. We're going to talk about some different properties of arithmetic. And the first property you see there is called the commutative property. Say that word with me, class. Commutative. Again, commutative. What's the root word of commutative? Does anyone hear a root word there?
Commute.
Commute. Does anyone know what it is to commute? It means to commute. Elaine, go ahead.
Like to go from place to place.
To go back and forth, right? To change places. For instance, I think your dad works at West Point, right, out of the Kia plant. And so he doesn't live there. He lives not too far from where I live. He drives up to the Kia plant for work, back home again. That's called a commute. Technically, I mean, even if you worked across the street, you're commuting to work. But, we think of it as a commute when you drive a little bit further, right? You go from one place to the next. You're changing your location. Well, we can do this changing of location with addition and multiplication. Look at the little example box next to the commutative property. We know this because when we learned our addition and multiplication tables as kids, we memorized 4 plus 3 equals 7. We also memorized 3 plus 4 equals 7. I mean, you did this with all your addition facts, right? 9 plus 2 equals 11. And somewhere else on the list was 2 plus 9 equals 11. And most of you, as kindergartners or first graders, started to realize, hey, these two numbers, it don't matter what order they're in, it's the same answer, right? Y'all figured that out already. Well, we have a name for that. It's called the commutative property of addition. That addends can change their order. Write that to the side, changing order. Write those two words next to where it says commutative property, changing order. You can do it with addition, you can also do it with multiplication, right? When you were learning your multiplication facts, your 3 times 5 equals 15. 5 times 3 equals 15. Hey, it's the same either way, right? So you learned that about multiplication. However, notice what it says in bold, subtraction and division are not commutative. You cannot change the order with a subtraction problem or division problem. For instance, what is 5 minus 2, class? 3. That's because if you have $5 and you spend 2 of them, you will still have $3 left. If you only have $2, can you spend $5?
No.
Not in cash, right? I mean, if you had a credit card, you could, I guess pay, but then you're going to be in the hole. You're going to be in debt, right? You're going to be at -3. Subtraction's not commutative. Division's not either, right? We could say 15 divided by 3. Well, class, that's 5. Maybe a better way to see it is 15 divided by 3 equals 5. But class, what's 3 over 15? 1/5. Right? 15 pizzas and only 3 people to eat them all. That's going to be a lot of leftovers. That's way too much. A bad example. But anyway, 3 pizzas and 15 people to eat them all. You're only getting a small fraction of a pizza and you're probably going to still be hungry, especially with junior hires. All right, so we understand, right? Division, subtraction, not commutative. Again, commutative, class, means to change order. You can rearrange it. Now, we did this already. To make our lives easier. Remember in the area of a triangle. What's the formula for the area of a triangle? Anyone?
1/2
A half BH. And so suppose we knew that the base of the triangle was 17 inches and we knew that the height was 10 inches. Well, rather than saying half times 17 times 10, we went out of order, didn't we? Because multiplication is commutative. We said, we're not doing it that way. We're going to take half of the 10. And we did that first to get 5. And then we multiplied to 17. We changed the order to do whatever was easiest for us. Because it's commutative. We could do the same thing if we were adding, and maybe you've done this before with a big old addition problem. I'm just going to show the ones place, but maybe there's a 7 and a 4 and an 8 and a 3. What I do is I say, well, I'm going to add the 7 and the 3 first. Class, that's 10. I'm going to add 4 plus 8, that's 12. And 10 and 12 give me 22, right? Where you can go out of order. That's commutative property that you're using. You've been doing it for a while. Now you know what we call it. It has a name. What is it, class? The
Commutative property.
The commutative property. Another property that you see there is called the associative property. Say that with me. Associative. Again, associative. Okay, someone besides Elaine, what's the root word of associative? All right, Bryson? Associate or associate. Have you ever heard of maybe in the business world, you know, the CEO talks about his associates, or this businessman talks about his associates? You ever heard that phrase? That just means the people he hobnobs with, right? His friends, his coworkers, the people in his group, right? Even at a small school like this, we still have little groups that sort of form, not because we're being mean to other people or anything like, well, I don't want to hang out with Bryson, but you know, maybe Luciana and Bryson don't have that much in common, so Luciana hangs out with some of the other girls, and Bryson, he hangs out with the boys. Maybe basketball players kind of hang together or something like that, right? Where you have little groups that you sort of form, and it's not cliquish necessarily, shouldn't be, but it's just, these are people I have a lot in common with. We like to hang out, we like to talk, right? We associate with different people. Associative property has the idea of changing, bless you, groups. Changing groups. Write that down next to where it says associative property. Bless you. Changing groups. You're regrouping, if you will, addends or factors. Really, this is kind of the same idea as the commutative property, because a grouping just means you do it first, right? Parentheses, exponent, parentheses, grouping symbols, we do those first. Well, because addition and multiplication can be done in any order, we could literally group things. So if it said 7 plus 4 plus 8 plus 3, let's just suppose for a moment this is how it was grouped. Well, it's not actually that bad. 11 plus 11, 22 really isn't too bad. But we could instead say, well, 7 plus 3 plus 8 plus 4. We could regroup things together. We kind of did this a lot when we got to the more involved surface area and volume formulas, right? Like even the volume formula we were working with yesterday, the volume of the cone. Ooh, anyone remember? I know we didn't have any homework, so long shot. Remember the volume of a cone formula, Kirsten?
V equals 2, pi r squared h.
Well, okay, the cylinder was pi r squared h, and we said that because the cone comes to a point, anything that comes to a point, we have to put what at the front? Anyone?
1/3.
1/3. So we said 1/3 pi r squared h. Well, let's suppose we knew that the radius was 6 and the height was 7. Well, we know, okay, well, I've got to square the 6 class, 36. So I've got a 1/3, I've got a 36, I've got a 7. And because of the 7, we said, well, the pi we're going to write class as 22 sevens. Remember, we can multiply any order we choose, right? So what we chose to do is, in a sense, we grouped the 1/3 and the 36, and we grouped the 22 sevens and the 7. Notice I'm using a raised dot for multiplication instead of a little X looking thing. And we said, we're going to multiply these two first, then those two next, and then we'll put it all together. Well, we're kind of changing the order, commutative property, but at the same time, we're also kind of grouping or regrouping the problem in a way. That's the associative property. Look at the examples that you see off to the side there. They have a 4 plus 3 plus 2. Well, technically, what you should do is you say 4 plus 3 is 7, plus 2 is 9. But I said you could, instead of grouping 4 and 3 together, you could change groups. You could say 3 plus 2 get grouped together. And so it's 4 plus 3 plus 2, which is 4 plus 5, which is still 9. Do we see that they both come out to 9 either way? But you're changing who the 3 is grouped with. First, the 3 is friends with the 4, then the 3 is friends with the 2, right? Really, we just be friends with everybody, right? So you can, how many would say, I'm like that, I can hang out with any group here at the school. I'm comfortable with everybody. You know, I'm just a friendly sort of guy. How many are like, no, I got my group, I don't need no. All right, let's not be closed-minded and unfriendly. All right, look at the multiplication. Same thing works, right? They took the same numbers, 4, 3, and 2. They grouped the 4 times 3, 12, times 2 is 24. Then they said, well, instead of that, let's make the 3 be friends with the 2. So 4 times 3 times 2. Well, then you multiply the 6, and 4 times 6 is still 24. Again, not subtraction or division. Just addition and multiplication are this way. Does that make sense? So with those processes, addition and multiplication, you can change the order, class we call that the commutative property, or you can change what is grouped together. That's the associative property. There's one last, oh, by the way, real quick, you can only regroup within the same operation. For instance, here, it's all multiplication, right? So you can change the grouping here. But let's say we took the surface area of a rectangular prism. Ooh, what's that surface area of the rectangular prism, Michael?
2LW plus 2WL.
Well,
I mean WH plus 2LH.
there we go. Okay, so what I can do, if I want to change the order within the multiplication and say h times 2 times L, I don't know why you would do that, but you could, right? But I can't say like, well, I'm going to pull this h over here and make this a 2WH squared plus, not separate operations. Within one operation, you can change that. Or if you said, well, I would have said 2LH plus 2WH and switch these whole things with each other. That's commutative property. You can change the order within operations. So these things are added, you can change them. But you can't pull something around. Does that make sense? Within an operation, you can do those things. The last property really isn't something you're going to use too much until later in algebra, though there's a kind of an interesting application, a little bit of that, and that's something called the distributive property. The distributive property. Obviously, the root word here should be pretty easy, class. Distribute. And what does it mean to distribute, Ben? For instance, if I said, I'm going to distribute donuts to the class, what does that mean?
Give away donuts to class.
Okay, so for instance, if I gave you a donut, and I gave Griffin a donut, and I gave Kirsten a donut, and I gave Joel a donut, and Michael a donut, Wayne a donut, Corey a donut, Luciana a donut, and Bryson a donut, did I distribute donuts to the class? Jalen?
No.
No, she's very offended back there, because somebody didn't get donut. That's not distribution. Distribution is when everybody in a group gets something. Now, if I said, I'm going to distribute donuts to the class, and should I go down to Miss Morse's class and give them donuts? No, they ain't part of this class. They don't need no. This class, right? This group gets donuts. We can do that with parentheses when there's a grouping. Look, for instance, at the distributive property with addition. If we have something like 4 plus 3 that's grouped and it's being multiplied by a 2, the 2 can be distributed to everybody in the group. Well, who's in the group? 4 is in the group, 3 is in the group, and they get 2. I know donuts are more fun than 2, but they get 2, meaning I'm going to multiply, because the 2 is up against parentheses, 2 times the 4, and I have to multiply 2 times the 3. If I only multiply the 2 times the 4, that's like Jalen over here, not getting any donuts. And that's not right, is it? No. Jalen deserves... Anyway, so we can multiply 2 times 4 and 2 times 3. Well, what is 2 times 4, class? 8. What's 2 times 3? 6. And what is 8 plus 6? 14. Well, that's going out of order of operations, isn't it? What if we followed order of operations? We would add first in the parentheses. We'd say 4 plus 3 is? 7. Times 2 is? 14. It's the same answer either way. But we could distribute. Look at the next example that they have there. They have a 5 outside the parentheses, and in the group, in the class, so to speak, they have 6 minus 4. Well, again, normally we just do 6 minus 4, class is 2, and then 5 times 2 is 10. But you could, notice what they did, they're looking in your book, at the top of page 99, we could say 5 times 6, class, 30. And we could say 5 times 4, and 30 minus 20 still gives us an answer of 10. Now again, why would we do this? Frankly, until you get to algebra, not much, though there are some interesting applications. If you drop all the way to the bottom of page 99, kind of a neat application here. They say, well, what if we had to multiply a 3 times a 492? That's a big problem. I don't know that it's that hard to multiply 3 times 492, but we could change the way 492 looks. We could change 492 and say, well, that's pretty close to 500, isn't it? It's just 500 minus 8. And so instead of multiplying 3 times 2, and 3 times 9, and carrying 3 times all that, well, we could do 3 times 500 in our head.
1,500.
1,500, right? 1,500. We could do 3 times 8 in our head. 24. And then we can subtract the 24 from the 1500 to get, what is that, 1476? Now again, same answer if we just, I'm just going to multiply the 3 straight up, you know, whatever. I don't know how if it's that much faster, but it's another way to approach it when working with numbers. So maybe some application, mostly you're going to see that when you get to algebra. Look, if you would, at the example problems on page 100 now. Turn the page. And they want you to solve the problem in the example problem, but use one of the properties. So we see the first thing they have is a half times 5 times 6. Now, order of operations says you multiply from left to right, which means a half times 5. Well, what's half of 5? 2.5. And then you multiply 2.5 times 6. We don't want to do that, right? Okay, 2.5 times 6. So what we do instead, class, is we rewrite the problem using the commutative property. And notice what they did says, forget 5 times 6, change the order. 6 times 5. Now it's half times 6, 3 times 5. Makes the problem easier, right? Commutative property. We could also do this. This kind of looks like 2 pi r, doesn't it? Yeah, 3.14 times 2 times 5. Well, I mean, we could do 3.14 times 2, class. 6.28. And then 6.28 times 5. Hold on, carry the... No, what's a better way? Start with grouping the 2 times 5, class. 10 times 3.14. All we have to do is go boing, and we get 31.4, right? Much easier sometimes if we regroup. Now, you say, weren't we kind of reordering as well? Well, technically, no. I mean, they still left the 3 numbers in the same order, but they just regrouped. They associated the 2 and 5 together. Again, the distributive property, this is a bit of a stretch, but maybe you resonate with this. 8 times 1,050? 8 times 1,000 and 8 times 50. 8 times the 1,000 is 8,000. 8 times 50 is 400. Now it adds easier 8,400. Again, it's a bit of a stretch, but you could use that approach in working with larger numbers, I suppose. Drop down now to the problems in the practice section. And number 1, they say 2 plus 5 is equal to 5 plus something. Now, don't make this too hard, class. 2 plus 5 equals 5 plus 2. What property did we just illustrate, class? Commutative, because we changed the order. So write commutative underneath number 1. Fill in the blank with the 2, and then write commutative underneath. C-O-M-M-U-T-A-T-I-V-E, commutative. It's also in the example problem, next to letter A. If you want to just look up the page a little higher. Look at the next one. They say 6 times 8 minus 5. Well, there's an 8 minus 5 in the class, and we're going to distribute 6, which means we multiply what times the 8, class? 6. And what times the 5? 6. Okay, what property is that? We didn't change what was grouped. We gave some 6 to everybody in the group. We distributed, like distributing donuts. Distributive property. Distributive property. Look at the next one. They say 2, what does that mean when they're up against each other, class?
Multiply.
Okay, so they say 2 times 9 equals something times 2. Well, obviously, class, what goes in the blank? 9. Okay, what did they do here?
Commutative.
Because they changed the order. They changed the order, so it's the commutative property again. Look at number 4. They said 9 plus 4 plus 6 could equal 9 plus 4 plus something. Well, what would have to go in the blank, class? We need a 6 right there. Now, did they change the order at all? No. The order in which you would do them, technically they did, but they didn't actually change the order in which they're written, so it's not commutative. They changed what the 4 associated with, didn't they? Instead of the 9 and the 4 together, now it's the 4 and the 6 together. So we would say that that's the associative property. How about number 5? What goes in the little blank, first of all?
3.
A 3 would need to go there, right? And that, once again, is the associative property. For number 6, they have an 8 times the quantity 1 plus 5. And they say, well, I could multiply 8 by something and then 8 by something else. Well, what are the 2 somethings we would have to multiply the 8 by, Bryson?
5. No.
1 and then 5, right? So in the blanks, we put the 1 and the 5. And which property are we seeing here on number 6, class? Distributive property. Does that make sense? Okay, kind of get the feel for these properties. Again, really we're just naming something that other than the distributive property we've already done. Look at number 7. They want you to fill in the chart with if you can use this property. Well, number 7, can we use the commutative property for 4 plus 8? Well, absolutely. 8 plus 4. We just changed the order. Can we use the associative property? Well, associative class changes what is grouped. Was there a grouping done yet?
No.
So can we change what's grouped?
No.
No, so you can't really use the associative property. Is there anything that's being asked to be distributed?
No.
No, there's no donuts. It's just the class, 4 plus 8. There's no donuts to be distributed, so we can't use the distributive property. What about number 8? Can we use the commutative property on number 8?
Yes.
Yes, how would we rewrite it, Griffin, with the distributive, or with the commutative property?
12 times 3.
Write that in the blank, 12 times 3. Can we rewrite it using the associative property, Joel?
No.
No, because nothing's grouped, so you can't change what is being grouped. Can you use the distributive property on this one here, Michael?
No.
No, there's nothing being asked to be distributed. Number 9. 4 times 9 plus 1. Can we use the commutative property here? In the parentheses, it says 9 plus 1, doesn't it? What else could we write in the parentheses instead of 9 plus 1, Elaine?
I'm scared.
Commutative property, change the order.
4 plus 1?
1 plus 9.
5.
So in the parentheses, just change it, make say 1 plus 9 instead of 9 plus 1. So you can rewrite it that way. 4 times 1 plus 9. That would be the commutative property, wouldn't it? Now, we didn't rewrite the whole entire problem, but just that portion, the addition portion, got rewritten. Or you could take the multiplication, and instead of this times this, you could take the whole thing that was at behind the multiplication, put it at the front. So how might, and it looks like that's what you were originally thinking of. What were you thinking for number 9 originally, Elaine?
So like 9 plus 1 times 4?
Right, 9 plus 1 times 4 is also a way we could rewrite that, right? So we could either do the addition commutative or the multiplication commutative. Can we rewrite it using the associative property?
Yes.
Yes. No.
There are parentheses, but can you change it instead of grouping 9 plus 1, maybe group 4 times 9? Because it's 2 different operations, can't you? If it were all addition, sure, you could rewrite it associative. If it were all multiplication, no, you can't rewrite that associative because you got 2 different operations going on at the same time. Does that make sense? And this is the one you've been waiting for. Can we rewrite it with the distributive property, class?
Yes.
Absolutely, because we have something being distributed to a quantity. The 4 is being multiplied by. Now, they actually use a little x thingy instead of pushing it up against the number, but they're multiplying a 4 times 9 plus 1. So how would we show it, Jalen? Distributing the 4 to everybody in the class.
4 times 9 plus 4 times 1.
Perfect. 4 times 9 plus 4 times 1. Does that make sense? We multiply each of them by the 4. Now, if we wanted to simplify it, we could, but that's not what we're doing right now. Number 10, we could rewrite that with the commutative property. There's a few different ways we could do it. Corey, give me one of the ways you see on number 10 where we could rewrite that with the commutative property.
2 times 7 times 5.
2 times 7 in parentheses times 5. Very good. He swapped what was in the parentheses since it was being multiplied. Luciana, do you have another way you can think of where we would rewrite that with the commutative property?
5 times 2 times 7.
Ooh, you could do both of them. Wow, so we put the 5 times, and she even flipped both of them. She put the 5 times first and the 2 times 7 in the parentheses. I was just thinking the 5 times 7 times 2 would have worked also. How about the associative property? Can we use that one? Can we use the associative property on number 10? Bryson? Yes, because it's all multiplication. So instead of grouping 7 times 2, we could group... Well, that would actually be changing the order too, though. That would be more commutative. So maybe keep the 7, then the 2, then the 5, but instead of grouping the 7 and the 2, group the 2 with the 5. So 7 times 2 times 5, right? So 7 times into the parentheses, 2 times 5 would be the associative property. Can we use the distributive property here?
No.
No, because the group has to have either addition or subtraction in it to distribute. We don't have that, so no distributive property on 10. The next section I like. Are these equal or are they not? If they are, why are they equal? Which property says here? Look at number 11. Is 77 plus 34 equal to 34 plus 77? Bryson, coming back to you. Yes, which property says they are equal? what did we do with the 77 plus 34 and make it a 34 plus 77? We changed the order. So which property is a change of order or change of location, if you want to think of it that way? Commutative property is the change of location. Look at the top of the next page, number 13. 4 minus 2, 2 minus 4. Equal or not equal, Griffin?
Equal. Wait, which one?
Top of the next page, 4 minus 2, 2 minus 4. Equal or not equal?
Not equal.
Oh, not equal. They tried to use which property here, Griffin?
Commutative.
Commutative. But can we use the commutative property with subtraction, class?
No.
No. Okay, look at number 15. 9 plus 4 plus 6 and 9 plus 4 plus 6. Might take you a moment here. Equal or not equal? 13 plus 6, 9 plus 10. Equal or not equal? Going down to number 15. What do you think here, Ben?
Equal.
Equal. They both add up to 19. Now, Ben, which property was used in making these things equal? What did we do? What did we change?
Associative.
We changed what was grouped. So yes, it is the associative property. Good. Number 17. 8 divided by 4 divided by 2. What is that, anybody? 1. Okay, 8 divided by 4 divided by 2. What's that, class? 4. Well, are those equal or not equal, class? Not equal. What did they try to use right there, class? They tried to regroup. They tried to use associative, but can you use associative with division?
No.
No. So they're not equal. Put a not equal to symbol. I don't remember if I've taught you this yet or not, but it's this one here. It's an equal sign with a slash through it. It means not equal. I think we've used that before. I can't remember. My classes run together. Look at number 19. 7 minus 3 minus 2. What is that? 2. 7 minus 3 minus 2. What's that?
6.
Oh, so class, not equal. What did they try to use? They tried to use the associative property again, didn't they? But can we use the associative property with subtraction, class?
No.
No. Do you see what we're doing on that little section?
Yes.
Equal or not equal? If they're equal, what property was correctly used? I want you to do the evens, 12 through 20. Put equal or not equal in the blank, and then if it's equal, tell what property was correctly used. Just put your arms through the sleeves. All right, pencils down. Number 12. 7 times 20, that's 140. 20 times 7, that's 140. Class, what should go in the blank? Equal. Why, Kirsten?
Because it's commutative.
Commutative property. Number 14. 3 times 2 times 7 gives 42. 3 times 2 times 7 also gives 42. Then we didn't memorize 3 times 14. So the art class, equal what property, Joel?
I'm lost. Where are
Number 14. The next problem you did. You did 2 through 20, the even, correct?
Yes.
Yes, and we just did 12, so the next one would be 14. What property was used on number 14?
Commutative?
Did we change the order of any of the numbers?
No.
No. If you look at the book, which would help right now, 3, 2, 7 was the order, right? The order never changed. So we didn't use the commutative property. What did change?
2 and 7?
Got put in class parentheses. They got put in parentheses. They hadn't been in parentheses together before. It's like the guy going out with the, anyway. So 2 is going out with 7 now. 2 used to go out with 3. They broke up. So anyway, he's now associating with somebody else. And so we would have the class associative property. Number 16, we have a 4 divided by 2 is 2. And then we have a 12 divided by 1.5 is, oh, heaven help us. But I know it's not 2. So class number 16 in the blank, not equal. They tried to use associative property. They can't do that with division. Number 18, 8 times 6 would be 48. 8 plus 40 is also 48. So class, in number 18, we should put equal. And what property was correctly used here, Elaine?
Was it distributive?
They distributed the 8 times the 1 and the 8 times the 5. Everybody got a little bit of 8. We distributed the 8. Number 20, we've got 8 plus 9 plus 7. Then we got 9 plus 7 plus 8. We actually used 2 different properties here. Give me one of the properties that was used, Michael. Commutative, because the order got all mixed up here. But we also, Jalen, used the associative property because we changed what was being grouped together. And they're both correctly done. 17 plus 7 is 24. 16 plus 8 is 24. They are equal. How many recognized on 20 there were 2 properties being used? Questions on those? Drop down to number 21 here, and you're going to see what look like formulas that we've been using. Okay? Except we don't have to do very much of the math. We just got to figure out some of the pieces and parts. Notice 21. 1/3 times 4 times 9. Nah. Class 1/3 times 9 times 4. Write that in that first blank. We can take the third of the 9 very easily, class, to get 3. And then 3 times 4 is 12. Look at the next one. 2 times 11 times 5 times 3. So annoying. Let's instead do 2 times the 5 and 11 times the 3. Because 2 times 5 is easy. It's, I don't love getting a 10. And of course 11 times 3, whatever, it's 30. But the point is I'm multiplying by 10, so all I got to do is go boink in class. We get 330. We're multiplying. Number 23. 0.5 really means what, class? Half. Okay, so half times 5 times 3 times 4, nah. Let's start with half times 4 and do the 5 times 3. Half times 4, 2. 5 times 3, 15. And so the 2 times the 15 gives us 30. Got ahead of me there. Look at the next one. This is one of the weird ones. But 3 times 297 could be thought of as 3 times what minus 3?
300.
300 minus 3. So 3 times 300 minus 3 becomes 3 times 300 minus 3 times 3. Are you following along with me there with the blanks? What is 3 times 300, class? 900. Obviously 3 times 3 is 9. They've already got that one in there. And 900 minus 9 is? 891. Again, you don't have to think of it that way necessarily, but you could. They did something interesting on 25 that, again, is really kind of unconventional. 993 is really close to 1,000, right? Everyone see that number? 993, really close to 1,000. How far away is it? It's only 7 away, right? So what they did was they said, well, I'm going to steal a little bit here. I'm going to turn 338, class, into 331 plus 7. But then I'm going to group the 7 with the 993 in the next line. So 993 plus the 7 plus 331. Well, 993 plus 7 is my 1,000. Nice, easy number I wanted. Plus 331 becomes very easy addition. 1,331. Now, you might be thinking, Mr. Dasky, I could have added 993 plus 338 so much faster. Yes, but I will say if you're trying to do it in your head, 993 is only 7 away. Let me steal 7 from that to get to the 1,000, stick with the remainder on. You maybe could do it in your head easier that way. Again, it's a bit of a stretch. Number 26 looks frighteningly like 1/2 pi r squared h, which we don't have a formula for 1/2 pi r squared h, but whatever. 1/2, and instead of half times the pi, class, let's do the half times the 8, and suck it up and do the 3.14 times 5 squared, which we should just write 25. Half of 8 is easy. 4 times 3.14 times, again, that 25. But then, let's save the 3.14 for last. And let's start by multiplying what 2 things? The 4 times 25. So put those in those next 2 blanks, because 4 times 25 is a nice, easy 100. And multiplying by 100 just means I go boink, boink to get 314. So again, these are properties, associative property, class, where we change what is Grouped. Commutative property, where we change the order. And the distributive property we really hadn't used much, but we could, I guess, to multiply by a grouping. Those properties, things we've been using this whole time. Your homework for this evening is to do page 102. Page 102, numbers 21, or excuse me, numbers 1 to 26. Page 102, numbers 1 to 26. Page 102, numbers 1 to 26. All right, have a wonderful rest of your day, and you are dismissed.